Hello everyone. The topic for today's video is going to be the project implementation of the battery management system for electronic vehicles. The project group members are as follows: myself, Sherwin D'Souza, Bryson Fernandez, Shibu Matthew, Sparsh Bindru, and the guide for our project is going to be Dr. Sapna Prabhu. The agenda for this video is going to give a small introduction about the project, followed by the problem statement, as well as the objectives that were accomplished by our team members, and lastly, a small demonstration video. So going ahead with the introduction, our BMS is going to have a very oversight of the battery pack, which would allow us to monitor the cells and upload the data to the cloud. The topology used for this BMS is going to be a distributed one, which would consist of master and slave boards. The main roles of the BMS are going to be to monitor the battery pack, sense the voltage, the temperature, as well as the current of the cells. We're going to be protecting the battery and ensure that it is a safe and operating state. We're also going to be providing a temperature fault if the temperature exceeds 60 degrees Celsius. We're going to be estimating the battery pack, that is basically having an SOC and SOH estimation, maximize the battery pack's performance, and also implement a data logging system. Moving on to stage 1 of the implementation, the problem statement is defined by the problem wherein the OEM BMSs or the BMSs available in the market tend to be rather very expensive, have some of the other faults causing a drastic measures such as fires to occur, and are very large and cumbersome, thus working with only specific type of battery packs. Thus our problem statement can be said wherein the OEM battery pack management systems are very expensive, thus designed for a certain standard specification of the battery pack. They also tend to have improper data logging and lack the live data acquisition, resulting in the inefficiencies of the battery pack, thus making them non-scalable as well as non-configurable. Moving on to stage 2 of the implementation, the objectives are going to be very simple, wherein we are going to be measuring the voltage parameters, temperature, as well as current parameters for the particular stages in the battery pack. All this data is going to be collected and then uploaded to the cloud, thus making it low cost and reliable to use. We're also going to make it robust against external factors such as EMI or electromagnetic induction, redundancies, etc. We're going to aim towards reducing the overall size and weight of the BMS, thus making it customizable and scalable for the particular project. Lastly, we're going to be implementing an ML model for the particular charge type estimation such as SOC or SOH estimation. Here you can see a simple block diagram of our particular project. Thus, we can go ahead and show our project workflow. The project workflow goes through first of all testing the project idea and making sure if the idea is feasible or not. Next, we'll be moving on to a more scalable option and implementing the idea using low-cost materials in a proper manner, such as making it on a breadboard. After that, we are going to be going in and showing the control and design master designs, thus creating the new PCB boards for testing. And also lastly, we will be having the final implementation of the project. Moving on to stage 3 of the implementation, as you can see in this block diagram, the final block diagram, the particular battery pack is first taken into the accumulator, having a charge and discharge circuitry around it. Parameters such as voltage, temperature, as well as current data are taken in by the slave board, which is divided into 3 main parts. The buffer circuit and the differential circuit are go ahead and work as a voltage monitoring circuitry, whereas the temperature monitoring circuitry is taken care by a thermistor. All this data is moved through a 16:1 mux, which is then passed into the final slave board controller, which is the ESP8266 module. This slave board controller then passes its data onto the master board using the RS485 communication modules. These communication modules go ahead and talk to the master board controller, which then takes in all this data and uploads this data to the cloud. It also makes sure that any irregularities in the data force a cutoff or force a shutoff at the particular master signals. Thus, our final implementation is divided into 4 main regions, wherein the battery pack is divided into an 4S1P configuration consisting of 18650 cells. The slave board consists of a flash module along with some complementary resistors as well as a thermistor for temperature monitoring. The daughter interface board consists of the MUX as well as the Arduino Nano for in our case as the slave board controller. And finally, the master board controller consists of the ESP8266 module as well as a current sensing module for uploading this data to the cloud. Here is the project video for our project implementation for this particular project.
So here is the project of battery management system. As you can see, this is the battery module which has been connected here. Moving on to the battery module, this is the slave module which you can see. Moving on to the slave module, this will be our daughter board for the master slave controller. Just to forego the broken Arduino Nano, we have used an Arduino Uno in its place. Using the RS485 connecting modules or communication modules, it has been connected to an ESP for the IoT communication. So here, step 1, we are going to be showing the actual reading values from the battery man. So as you can see on your screens, the battery performance field monitor is being read 4.2 volts, and correspondingly on the Adafruit dashboard you can see that the cell voltages are all being correctly manipulated. But let's say, for example, our battery values are coming 0, so let me remove this a little bit. So as you can see, I've taken it a little bit of tilt, disconnecting one of the cells. So because of that, the temperature goes, this cell voltage goes below, and once the cell voltage goes below, you can see that yes, Adafruit has given the database, Adafruit has reflected the change. So connecting the battery back to normal. Next, we can go ahead and simulate a change in temperature using this NTC module right here. And we have a lighter for demonstrations. So as you can see that once I keep it closed, the master board is going to be detecting the change. And as you can see, the temperature has gone above the threshold, and the change in the Arduino is detected that yes, the temperature has become too hot. So by the time we cool this down, change in temperature should occur. And as you can see, it is all good now. Let's come back to nominal temperature.
Once the data has been taken into our ML model, the ML model then uses random forest regression to train itself and train the neural network for the SOC and SOH estimation for our battery pack, as you can see in the graph shortly.
Moving on to stage 4, the final stage of a particular implementation. The final outcome can be stated as the SOC prediction using machine learning and deep learning models. As you can rightly see, the real SOC follows very closely to the predicted SOC as given by our neural networks, both by a random forest as well as feed-forward neural network. We are getting an accuracy of around 99.8%, thus proving a particular model has been trained correctly. Thank you for watching the BMS EV video.